to solve the first problem of the second partial of electricity and magnetism that says like this. A cylindrical insulating shell of infinite length with internal radius r. So here we have our cylinder that goes that way. Here is our internal radius r. And external radius v, its external radius, has a uniform volumetric charge density. So here we have density. A line of uniform linear charge density of lambda. So here we have lambda in this point through that way is placed along the axis of the shell. Determine the electric field everywhere. So we have to determine all the electric field, and for determining we have to divide this cylinder into three parts. The first part is this part in here, that it's only including lambda and the part of the axis. The second part is here in the cylinder itself, that includes S, that it's S2, and includes our density of phi. And our third part is this part in here, that is S3, that includes everything. So for obtaining our electric field, we have to determine first one by one. So for determining the first electric field, we have to obtain the electric field by determining that the electric field times the area is equal to the enclosed charge over our constant. But the area will be exactly the same as 2 pi r L. This is the area of the cylinder. And this will be exactly the same as lambda, that is our linear density, times the L, that is the length of the cylinder, divided by our constant. So our electric field 1 will be equal to lambda over 2 times pi r, and our L's get cancelled because we have it in both sides, times our constant. And this is the electric field for the first part. For obtaining the electric field for the second part, I'm gonna do it this way. We will have to use this exact formula that says that our electric field times our area, that will be exactly the same, 2 times pi r L, will be equal to, we have to use two different things, the hollow part and the part of the cylinder, because we are using the S2. So we will have to obtain first our density for the cylinder part times our volume divided by our constant, plus the linear density of the axis times the length of the cylinder divided by our constant. So this, as we write it here, will be equal to 1 times our 1 over our constant, our density, times, and here we have to write the formula of the volume of the cylinder, that is pi r, that is the radius, square lambda minus pi a square lambda. Here I write a square because it's the small radius, and here I write r because this is all the part, all the cylinder itself, and this is only the whole of the cylinder. So once we have this, we have to sum lambda L over our constant. Once we have this equation, we get dA in this part, and we obtain that our second electric field is equal to lambda here plus our second density times pi by r squared minus a squared, and this all over 2 times pi, our constant r. And this is the result for our second electric field. And for our third electric field, we will use exactly this same part and this same part, but our volume will change. Why? Because we are not just only using till this part of the cylinder, we are considering all the cylinder itself. So I'm going to write that the electric field times 2 times pi times r times L, it's equal to the sum of our density, the volume, all of all the cylinder divided by the constant plus lambda L divided by the constant. And this will be equal to 1 divided by the constant, and this all multiplied by our density times pi a squared L. Here we are using a because it's the internal radius, that is all the cylinder itself, minus pi b squared L. This is using the whole cylinder, and this plus lambda L. And this way we are not just only obtaining one part of the cylinder, as here we wrote R because we are using only one part of the cylinder. Here we are using from the beginning of the cylinder to the end of the cylinder. And to obtain the final value of the electric field, we will say that it's lambda plus our density times pi b squared minus a squared divided by 2 pi times our constant times r. That is almost exactly the same as this part, but we are changing b for r. And this is how we solve this problem.